The carburetor. It meters and delivers fuel to the engine under all conditions. How does it function? It is made to function by air, drawn through the air intake by the engine. The speed at which the air moves through the carburetor is determined by the speed of the engine. This model demonstrates the principles involved. It consists of a tube, at the center of which is a restriction called a venturi. Air is drawn through the model in the same way that an engine draws air through a carburetor. If smoke is introduced into the model, the movement of the air may be seen. Liquid is drawn up into the main airstream and broken into tiny droplets. This is what happens in a carburetor. In a simple single-jet carburetor, there would be a venturi, a throttle, a jet, and a float chamber, which contains the petrol. The flow of air through the venturi causes a pressure drop, which pulls petrol from the float chamber through the jet into the airstream. The flow of fuel is controlled by the difference between pressure at the nozzle of the jet and the atmospheric pressure in the float chamber. The size of the pressure drop governs the operation of the engine, which responds to the position of the throttle. Such a carburetor is only the beginning. It does not meet the needs of the modern motor car. It was good enough for a car like this. But it wouldn't begin to work in one like this. Developments of the petrol engine have produced efficient and sophisticated carburetors to meet the demands of modern motoring. The job is to deliver the right mixture of fuel and air to the engine under all conditions. And to keep the mixture in the correct proportions, more air has to be introduced. This is done by an air bleed, which restricts the amount of fuel reaching the engine by mixing in more air to maintain the correct mixture. The air bleed consists of special channels within the carburetor, and the flow of fuel through the main jet draws in the additional air. When starting from cold, a richer mixture is needed. Here the choke plays its part. To start the engine, the choke is closed, which slightly opens the throttle. The choke valve allows very little air to pass. So when the engine is turned over, the suction acts mainly on the fuel jet, and together with the small amount of air, produces a richer mixture for starting when cold. At normal idling speed, the airflow is not strong enough to pull sufficient fuel into the venturi to keep the engine running. To do this, a small amount of petrol is injected into the side of the throttle nearest the engine. This is the idling jet. Petrol is delivered from the float chamber, air is drawn from the upper part of the venturi, and sufficient mixture is provided for the engine to idle. In normal acceleration, a progression jet provides more petrol until the main jet takes over. Sudden throttle opening provides more air, but weakens the mixture. There is a lag whilst extra fuel is drawn into the venturi to meet the new conditions. And the accelerator pump, by injecting a quantity of fuel into the airstream, restores the mixture strength, and sharp acceleration can take place. Essential in conditions like these. There is another type of carburetor. It is called a variable jet carburetor. One side of the venturi is replaced by the bottom of a piston, which moves up and down in a finely machined cylinder. When the engine is at rest, the pressure on both the underside and top side of a piston is atmospheric, and therefore equal. With the engine running, air is drawn out of the interior of the dome. The pressure falls, and the piston is lifted by the greater atmospheric pressure below. When the engine stops, the air flows back again, and the piston falls. Air pulls droplets of petrol into the venturi, and to regulate the flow, a graduated needle is held by the piston in the jet. As the throttle opens, air is drawn through the carburetor, the piston rises, and the fuel that is needed is pulled into the airstream. For cold starting, there is a disc valve, operated by the choke, in which a series of holes of different diameters are drilled. The choke control rotates the disc, and in the full rich position, all holes are open to the flow from the float chamber. As the engine warms up, the choke is pushed back in. Fewer and smaller holes provide the fuel, and the mixture returns to normal. The carburetors we have described are only two of many kinds. Although the principles are the same, individual engine requirements have produced many modifications of design and manufacture. In higher performance motor cars, maximum power is obtained by drawing in as much mixture into the cylinders as possible. A single carburetor is not always sufficient for this purpose. And one development which meets the need is the twin choke carburetor. It consists of two carburetors of different diameters side by side in the same casting. At lower revolutions, the needs of the engine are met by the smaller carburetor. At higher revolutions, the larger diameter carburetor comes into operation, greatly increasing the flow of mixture into the engine and improving its performance. The task is always the same. It is simply to deliver the right mixture of fuel and air to the engine at precisely the right moment.